Okay, for this problem, I'm telling us that C is the boundary of this triangular region here. So it's the triangle with vertices at the origin, 2, 0, and 0, 1. It's oriented counterclockwise. Okay. We've got this vector field, x squared, xy, and I want to evaluate, oops, I should have put a C there. I want to evaluate the work integral I get using f going around C. Okay. Now, if I were to do this as a line integral, I would have to do 3 integrals because there are 3 separate line segments that make up the curve C. It is piecewise smooth. It comes in 3 pieces. This is a great time to use Green's theorem instead because those 3 boundary pieces enclose one region. D would just be that solid triangle. So I can just do one double integral over D instead. And let's see, to see what I would integrate, I'm going to just use the shortcut because I'm so bad at memorizing things that I just take this 2 by 2 determinant, my 2 partial derivative operators in alphabetical order, and then the components of f, x squared and xy. So I'm getting the partial with respect to x of xy, which is just y, minus the partial with respect to y of x squared. Oh, well, that's just 0. Cool. So I'm integrating over d just y dA. So I probably want to now write this as an iterated integral. I think I'm going to slice d this way, and that way I can say my slices are going to go from 0 to 2. Along each slice, my y value goes from 0 to the y value on this line. So let's get that line. Looks like the slope is -1/2, and the y-intercept is 1. So I can say this is going to be the integral from 0 to 2, integral from 0 to -1/2 x plus 1 of y dy dx. So that's integral from 0 to 2. Antiderivative of y with respect to y is just y squared over 2. I'm evaluating that between -1/2 x plus 1 and 0, and then we'll integrate that with respect to x. So I'm going to get the integral from 0 to 2 of -1/2 x plus 1 squared over 2 minus 0, and then we've still got to integrate that with respect to x. I'm going to just factor out that 1/2. I get 1/2 integral 0 to 2 of -1/2 x plus 1 squared dx. Now I could, at this point, FOIL that out. I could do the arithmetic and multiply out -1/2 x plus 1 times -1/2 x plus 1. If I'm feeling a little tired, though, I could notice that if I just did a u sub, my u prime is just -1/2. It's just a constant. So I may not have anything outside of this function composition, but if all I need for my du is a -1/2, I can easily introduce that. I'll introduce a -1/2 here, counterbalanced with a -2 on the outside. Of course, the 2 and the 1/2 will cancel. I suppose I could have just kept that 1/2 on the inside if I wanted to, but it will now be a negative that I have. So let's see, we've got negative, the integral from the u value at 0 would be 0 plus 1 is 1. To the u value at 2 is going to be -1 plus 1, which is 0. But then it just becomes u squared du. So that's going to be -u cubed over 3, evaluated between 0 and 1. Do just be careful, the 0's on the top now. So that's -0 minus 1/3. That's -1/3. That's going to be 1/3. So nice example of how Green's theorem can be a time saver, particularly if your boundary curve is piecewise smooth so that you'd have to do multiple integrals, and also just a neat trick to avoid a little bit of algebra. You can do a little bit of calculus and do a u substitution instead of foiling out to square that binomial. totally up to you. If you prefer to multiply it out, that's totally fine. Both methods are correct.